Here we have a classic volume problem where we will find the maximum volume of a box that is formed from a sheet of cardboard of 14 inches by 10 inches, and we will cut corners out where the shape of each corner will be a perfect square. We don't know the dimensions, so we will label each square as x by x. And if you imagine cutting out each of those squares from the corners, we're going to have this cross-type shape where we can fold up each of those edges. And once we do that, we should form a box of some type of shape close to this, where the height of the box is that dimension x. If you imagine taking that edge from the previous shape, folding it up, that would form that dimension x. The length is easier to imagine. You had that 14-inch length from the sheet, and when we subtracted an x from each corner, and we'd be left with 14 minus 2x, since we subtracted an x from the left and from the right. The width was originally 10 from that sheet of cardboard, and we subtracted an x from each corner as well. There we have all three dimensions labeled for the box. Next, let's build the volume equation. The volume of that box in terms of x is represented by length times width times height, where the length is 14 minus 2x. The width is 10 minus 2x, and the height is x, and that being the monomial term, I like to write that in the front. Let's distribute. I'm going to distribute first by filling out the last two binomials. 14 times 10, 140, minus 28x, minus 20x, plus 4x squared. And distribute completely. I'm going to simplify and distribute the x at the same time. 4x squared would be the first term multiplied by x. I'm going to write that as 4x cubed first. For standard form, we have a negative 48x in the middle times an x, which would make a negative 48x squared. And then that 140 gets multiplied by x, and we'll call that 140x. So there's our polynomial in standard form for the volume equation. We want to take the derivative of volume. We're going to write that as v prime of x, the derivative of the volume with respect to x. And we do this so that we can find the critical value. This is equal to 12x squared minus 96x plus 140. Next, we set the derivative of the volume equal to 0. You set your derivative equal to 0 to find your local max. And we're trying to find the maximum volume after all. Next, I'm going to recommend going straight to your quadratic formula to be able to solve this quadratic equation. I'm going to rewrite this as the form of x equals negative b, which is negative 96, positive 96, plus or minus the square root of 96 squared, since that negative 96 squared becomes positive, minus 4 times 12 times 140, all over 2 times 12. And then going straight to my calculator here, I'm going to plug each of those in one at a time, plugging in the plus sign first, 96 plus the square root of that expression, all divided by 24, would give us 6.082, and then plug in the 96 minus the square root of the rest of that expression, all divided by 24, to find the other answer, because those are two different solutions here. The other solution being approximately 1.918. I encourage you to verify those by quadratic formula. Next, we only need one solution here, and one of these numbers does not make sense. It's not in the domain, and if you check with the 6, if x is approximately 6.082, that does not make sense in the domain of this box because the width is 10 minus 2x, and if x is 6, we have 10 minus 2 times 6, which gives us a number close to negative 2. We can't have a width of a negative 2. That's not reasonable here. It doesn't make sense for the context. So the only reasonable value we have here is 1.918 for x. Don't forget that x represented the height of the box, so we represent that height by 1.918 inches. And that stands for the value that gave the maximum volume.